Welcome back to the channel. This is part 2 of the fine-tuning series. In the previous video, we focused on the concepts. We looked at the difference between full fine-tuning, PEFT and LoRA using visuals. In this video, we are going to turn all of that into a concrete step-by-step implementation. We are going to use a real model from HuggingFace named BART large CNN. This model is a sequence-to-sequence transformer model that's been pre-trained for summarization. It takes an input text and generate an output text. We'll start by using it as is, then we will fully fine tune it, and then we'll repeat the training using PEFT and LoRA so you can see the difference in practice. The structure of the video is simple. We'll first explain a few terms that we will be using like tokenizer, sec-to-sec model, learning rate, epochs, etc. Then we'll work through the notebook from top to bottom, loading the dataset, running a baseline, doing full fine-tuning, evaluating it, and finally switching to LoRA for parameter efficient fine-tuning. Before we dive into the code, let me quickly define a few terms you are going to hear me repeat. A pre-trained model. It's a model that's already been trained on huge corpus of text. In this case, BART is one of those. Rather than starting from scratch, we are fine-tuning this pre-trained model on our specific summarization task. Next is a tokenizer. It's a component that turns text into numbers, into tokens that the model can understand. Every model comes with a matching tokenizer, and it's really important to use the correct pair. The next term is sequence-to-sequence or sec-to-sec model that takes a sequence as input and produces another sequence as output. For example, from a conversation to a summary or from English to French. Next term is a learning rate. This is how big each update step is when the model learns. High learning rate means big steps. It learns faster, but it can easily overshoot. Low learning rate means small and careful steps, but maybe too small. So there should be a balance. Next term is an epoch. It's one full pass through the training dataset. If you train for one epoch, the model has seen each training example just once. Next term is the batch size. It's how many examples the model processes at once before updating its weights. Larger batches are more stable but require more memory. And the final term is ROUGE. It's an evaluation metric for summarization that measures how similar the model's summary is to a human summary. With those in mind, let's jump into the notebook. Okay, for fine-tuning, I'm using ML M52X large instance on Amazon SageMaker AI, and this is where my Jupyter notebook is running. Okay, so we start by importing the libraries we need. Everything here comes from either Hugging Face or PyTorch. I have already installed these libraries using pip install. So just in case you see an error that you can't find a particular library, please go ahead and do pip install that particular library. Before we start coding, let me quickly walk you through the dataset we are going to use. This is the DialogSum dataset hosted on Hugging Face. It's a collection of real conversation dialogues along with the high quality human written summaries. Each example in the dataset has three key fields, dialogue itself, the summary, and the topic label. The dialogues are typically multi-turn conversation between two human beings or maybe multiple human beings. So it's a great data set for training models that need to understand back and forth interaction and then condense into something short and meaningful. Okay, so let's load the data set on our Jupyter notebook. So we use load dataset library, which downloads and prepare the dataset for us. When I print it, you will see the familiar train, validation, and test splits. Each example contain dialogue, a summary, and a topic. This is the same structure that we just saw on Hugging Face website. Yeah, you can see that it has three sections, each containing ID, dialogue, summary, and topics. We load the Facebook BART large CNN model like this. So this is the model name. Then we first create the tokenizer. This knows how to break the conversation and the summary into tokens in a way that matches the BART vocabulary. Then we load the model itself using this library. Notice that I pass BF float 16 here. It will work even without this section, but this tells the PyTorch to store the weights in B float 16 instead of 32, which gives lower memory usage, which is usually very similar accuracy, especially on modern hardware that support B float 16 natively. So this is a way to save the memory. So I'm going to run it now. So we are loading the model now. Next is defining a helper function called number of trainable parameters. This loops over all the parameters in the model, counts how many there are in total and how many of them are marked as trainable. When we print this for the base model, all the parameters are trainable because we haven't frozen anything yet. This is our full fine-tuning scenario, so we are about to update the entire network. So when we run it, you can see that the total parameters are this many and the trainable and the total parameters are same. Okay, so before we touch any weight, we run a quick baseline. We pick an example from the test set. Here I'm using index 200 and I print out the raw dialog, the human summary and the topic. Then we build a simple prompt like summarize the following. This is called a zero shot inference. And then we tokenize it. So first we are going to print what we have in 200's index. So this is the dialog, this is this is the human summary, and this is the topic name. Okay, so now we will prepare a prompt which is for zero shot inference. That's how we write it. So summarize the following, and then we pass the dialog, and we are instructing the model to give us the summary. Then we first create the tokenizer and then pass it into generate function, tell it to produce about 200 tokens as output and decode the output back to human readable text. And then we will print the output from the BART model without any fine-tuning on dialog specific data. That's our zero shot baseline. It's what the model can do out of the box. So let's run it. Okay, so the human summary is that person 1 teaches person 2 how to upgrade software and hardware in person 2 system, whereas the model zero shot says you would probably need a faster processor to begin with, and you also need a more powerful hard disk, more memory, a faster modem. You might also want to add a CD-ROM drive too, because most new software programs are coming out of CDs. It would allow you to make your system on flyers and banners. Next, we define a preprocessor function which prepare our dataset for training. So this is the definition of the function. For each batch of example, we build a prompt that says summarize the following following conversation, and then we append it with the dialog and end it with the summary. Here we call the tokenizer on each of those prompts with padding set to max length of 512. We also tokenize the reference summaries into labels, again with padding and truncation. And then this function returns the batch. The key idea here is the model sees the prompt plus the dialog and is trained to produce the reference summary. After this step, every example in our dataset has an input ID, IDs, and a label, which is exactly what the trainer expects. Next, we apply the preprocess function to the entire dataset with map function. We ask it to work in batches so it's efficient, and we remove the original text column that we no longer need. The result is tokenized dataset where each example is already numeric and ready for the model. Next, we create training arguments. This block controls the behavior of training. That's what it is. So output directory is where all the checkpoints and logs will be stored. The learning rate is set to this, which is quite small. That's intentional because we are updating the entire BART model, hundreds of millions of parameters. If we use a huge learning rate, we could destabilize the model. We also set the num train epoch to 1, which means that the model will see each training examples once. For example, for a real project, you might increase this, but here we just want to demo the pipeline. Weight decay 0.01, which adds a small penalty on large weights to reduce overfitting. Logging steps equal 1 means we will log the loss every step, which is useful for debugging purposes in case we want to troubleshoot why something is underfit or overfit or why something has gone wrong. max step equals to 1 is your notebook. Essentially make this quick demo run. It limits the training to single step, which keeps the demo fast, but obviously is not enough for high quality model, and it's not recommended for production environment. In real run, you would remove or increase that. These arguments collectively define how the optimization happens, how fast we learn, how often we log, how long we train. Next, we create a trainer object. We give it the model, the training arguments, the data collator, and training and evaluation datasets. When we call trainer.train, the trainer handles everything. It loops through the training dataset, build batches, compute the loss, back propagates, and updates all the trainable parameters in BART. Because this is full fine-tuning, every layer in the network gets updated. You can mentally connect this to the leftmost column of the diagram from video 1, where all the blocks turned into updated layers. So let's run it and also start our training. So this step is going to take some time, so I'm going to pause this video here and come back once this is all done. Right, the training has finished. Here you can see the training output. This block gives us a quick snapshot of what actually happened during the fine-tuning run. You will notice that global step equal to 1. That's because in this demo, I intentionally limited the training to a single step. If you remember, we had just one epoch. And max step equal to 1. So that's why the global step is equal to 1. In a real training run, you would allow this to run for maybe thousands of steps or multiple epochs, but for our walkthrough, this is enough to show how pipeline works end to end. The key number here is training loss, which is showing 11.18. Loss is measure of how far off the model's predictions were from the correct summaries during the training. With only one training step, this number will naturally be very high, but if we trained for longer, you would typically see this loss go down significantly as the model learns. Below that, we have a few runtime statistics, like train runtime tells us the total time training session took, which is like 124 seconds. The training samples, train samples per second, and train steps per second. These numbers are also extremely low because we trained only a tiny sample and only took one optimization step. In a proper full training run, as I said before, these values would be much higher. The total flows is a technical metric showing the total floating point operations used during training. You don't usually need to interpret this directly, but it gives an idea how much computation went into the update. So the main takeaway is that the output confirms that the training pipeline worked correctly, and if there were a real fine-tuning job, you would see hundreds of thousands of steps here, shrinking loss values and much higher throughput numbers. But for our demo, the light training step is enough to validate that everything wired up correctly. We now define a helper function to upload directory to S3, which takes a local directory and uploads each file to a specified S3 bucket and prefix. It's a simple but practical way to store your trained model somewhere permanently or share with other systems. So the fine-tune model is currently stored in this directory. I'm going to pick it up from here. First, I'm going to save this locally and then uploading it to S3. So to save it locally, I'm gonna use this command. Now I'm going to upload it to S3 using the helper function we defined. So the upload is done. I'm now reloading the model. So reloading the model is a good sanity check. If this step works, this means the model was saved correctly and is ready to be used in production or for further experiment. Now comes manual evaluation, original versus the fine-tuned model. Now we repeat the earlier experiment on the same dialog, which was on 200th index. We print the human baseline summary and then use the original model to generate a summary. And then we use our fine-tuned model to generate another summary. And we print them all three, one after another. This is where you can visually or manually inspect how the fine-tuning changed the behavior. Sometimes we improve a lot and the improvement is obvious, and the fine-tuned model sounds more concise or more focused on the key points of the dialogue, but sometimes it underperforms. So we will see how it goes with our fine-tuned model. So this is a function. So I'm getting my 200th index, and then I'm getting the human summary from the dataset itself, and then I am passing the zero-shot inference prompt, producing the original model summary, and then I'm using my fine-tuned model, which is here. This is the original model summary, and this is the fine-tuned model summary. Yeah, and I am going to run it. Okay, so the human summary is something we already have seen. That's the original model summary. And that's our fine-tuned model summary, which says you could consider adding a painting program to your software. It would allow you to make up your own flyer and banners. So this is the manual evaluation. We might not be able to see the difference. Let's use ROUGE matrices and see the difference. Okay, so next we load the ROUGE matrix like this. We first take the 10 dialogues from the test set. For each one of them, we generate summaries using original model and fully trained model, fully fine-tuned model. We then compute the ROUGE score for both. So that's my code here. So we are taking 10 from the test datasets, and then we are looping through it, and then we're running it via our fine-tuned model as well as original model. So let's run it. Okay, now we run it. So these are the results of the ROUGE matrix. So we compute the ROUGE score for both of these. So ROUGE 1 measure the overlap of individual words, ROUGE 2 measure the overlap of word pairs, and the ROUGE L measure the longest common subsequence. So higher scores indicate that the generated summary is closer to human one. So we are just waiting for it to generate ROUGE 1, ROUGE 2 and ROUGE L scores for us. So finally, we compute the absolute percentage improvement of the fine-tuned model over the original model. This gives us clear numeric sense of how much fine-tuning helped us. So I'm going to pause this video while it's calculating the score, and I'll come back once this is done. It has returned us ROUGE 1, ROUGE 2 and ROUGE L values. We are now going to calculate the percentage that I mentioned just now. So you can see that the ROUGE 1 returns 21.72. This is the absolute percentage improvement of fine-tuned model over original model. So you can see that ROUGE 1 is 20%, 21% improvement, ROUGE 2 says 6%, ROUGE L says 14%. So it has improved with the full fine-tuning. So now we will move to the PEFT and LoRA. At this point, we have seen how full fine-tuning works. We trained all the parameters and we improved performance, but at the cost of updating the entire model. We are now going to repeat the same process with PEFT using LoRA. The idea is to get comparable performance while training only small fraction of parameters, which is cheaper and faster and easier to store. So let's move to the PEFT. So right before we touch the code, it's worth restating what PEFT with LoRA does. Instead of updating every weight in the BART model, LoRA injects small low-rank matrices, additional parameters into selected layers. During fine-tuning, we freeze the original BART model weights and we only train these new LoRA parameters. So conceptually, full fine-tuning rewrites the whole book, whereas LoRA just adds small sticky notes inside the pages. The base book stays the same and the sticky notes capture all the task-specific tweaks. So we are going to import some libraries here. And we will now define LoRA configuration. So the most important parameter here is R, the rank. This controls the size of low rank matrices. A smaller R means fewer parameters and it's lighter and faster, but potentially less expressive. A larger R gives adapter more capacity, but costs more memory and compute. Here we set R is equal to 32, which is a reasonable compromise. Call get PEFT model function with the base model and LoRA config like this. This should return a new model object that behave like BART but has LoRA adapter inserted into it. So that's how we call it. When we call number of trainable parameter function that we defined up here, this function on the PEFT model, you would see there is a dramatic drop in the trainable parameters. Only LoRA matrices are trainable now, often around 1% or less of the total model weight. So I am going to call going to print the trainable parameters here. So you can see that it's very less, which is around 1%. We then define a simple, a custom trainer class. You may have option to just go with the trainer class, but I have defined a safe trainer class that is a subclass of trainer and slightly tweaks the training steps. So the main idea is to filter out any unexpected keys in the batch, so we only pass valid arguments into the model's forward method. This prevents some tricky errors when working with the customized dataset. So we now define a new training argument for our PEFT model for LoRA training. Notice that the learning rate is much higher now because you are only training a small set of parameters. We can afford to move faster without destabilizing a huge network. So we again train for one epoch with logging every step and limit steps in this demo run. Now we create a safe trainer instance passing in the PEFT model, the training argument and the tokenized trainer dataset. So that's how we do it. PEFT model, the arguments, the collator, and the dataset. When we called PEFT trainer.train like this, we are now only the LoRA parameters get updated, the base BART weights remain frozen. So now that the training is complete, I am not going to talk about each one of this. We have discussed it with the full fine-tuning output, but here I just wanna bring your attention to the train runtime, which is just 37 seconds, and as opposed to 124 seconds in the previous in the full fine-tuning run. We are going to save the PEFT model locally like this, and we are also going to upload the model to S3. Next, we reload the model again fresh, like we did with the full fine-tuned model. We also recreate the tokenizer. Then we wrap this base model with PEFT from pre-trained. We set the is trainable equal to false this time because at this stage we are only doing inference, not training. If we check the trainable model count now, trainable parameter count now, it should say 0, which confirm that all the parameters are frozen and there is no room for training. So you can see that they are 0. The number of trainable parameters are 0 now. Now comes the fun part. We compare all three models side by side. We again pick the model index model dialog at index 200, generate 3 summaries, one from the original model, one from full fine-tuned model, and one from PEFT LoRA model that we just fine-tuned. Then we print the human summary first to act as the ground truth. Then we print the original model's output, then fully fine-tuned output, and finally the PEFT model's output. In many cases, you will see the LoRA is very close to fully fine-tuned model with only minor differences, but let's see how it goes in our case. So I'm going to do the same, getting the same 200 index, preparing a prompt, then generating the output from the original model, then full fine-tuned model, and then PEFT, and then we are printing it side by side. So this is the baseline, original, and full fine-tuned, and the PEFT model. Now to make the comparison precise, we once again compute ROUGE score, but this time for all three models across a small slice of test set. In the previous example, we took first 10 sets from the test dataset. We are going to do the same. We iterate over 10 dialogues again, and we are going to print it. So this is going to compute the ROUGE score for the original model, the fully fine-tuned model, and the LoRA PEFT model. Okay, so this is the ROUGE metric evaluation of original model and the fine-tuned and PEFT model. Finally, we will calculate the absolute percentage of improvement of the PEFT model over the original model. While the PEFT LoRA model shows a slight decrease in the matrices compared to the fully fine-tuned model, this trade-off is expected and often acceptable because the small drop in performance is compensated by significant efficiency gain. LoRA trains only a small fraction of the model's parameter and drastically reduce the memory usage and compute requirement and training time. This means you can fine-tune large models on single GPU or a limited hardware, making it ideal for quick experimentation or resource-constrained environments. In many practical applications, this minor performance difference is negligible when weighted against its cost and scalability benefits of PEFT. And that's the full end-to-end journey. We started with a pre-trained BART summarization model, ran a zero-shot baseline, performed full fine-tuning, evaluated with ROUGE. Then we switched to PEFT with LoRA, retrained only a tiny subset of parameters, and compared all three models. If you have followed along until here, you now have a complete template to fine-tune your own model, whether that's only for email summarization, support tickets, construction reports, or any kind of text. If you found this useful, don't forget to like the video, subscribe, and let me know in the comment what kind of fine-tuning tutorial you would like to see next.